We're beginning the third and final part of Lesson 4, Finding Limits by Analytic Methods. And in example 5, we're going to look at the rationalization technique or the conjugate method. So the technique of rationalization can be used to find the limit when there's a radical in the numerator or denominator. So as you can see, we have the graph that's shown there for our function of g of x, which is the square root of x plus 2 minus 1 over x plus 1. So how do we find the limit at -1? So we can see from the graph that we should be at this point, and that point is at -1, and that's looks like about a half. But it's hard to tell exactly from the graph. Is it a half? Is it, I don't know, somewhere close to a half, like 0.4, 0.3, 0.6. So you want to just be careful. So analytically, we can do this and get an exact value. So we're going to, as it says above, we are going to rationalize. So by doing that, our limit is going to look like this. We're going to take this part of the limit and we're going to multiply it by the conjugate, which will be the square root of x plus 2 plus 1 over the square root of x plus 2 plus 1. And when we do that, what we get is the limit as x approaches -1 of x plus 2 minus 1. And in the denominator, we're just going to leave it the way it is for now. We're going to have x plus 1 times the square root of x plus 2 plus 1. Okay, simplifying, we get the limit as x approaches -1 of x plus 1 over x plus 1 times our conjugate. And you can see this is a very nice thing because the x plus 1's will cancel. So our limit simplifies to 1 over our conjugate. And let's try direct substitution now. So we're going to get 1 over the square root of -1 plus 2 plus 1. So we get 1 over the square root of 1 plus 1. So we get a half, which is exactly what we predicted from the graph. So therefore, we can say with certainty that the limit as x approaches -1 of g of x is going to equal 1/2. Okay, so doing another one where the radical's in the denominator, it's the same idea. So what we're going to do is we are going to multiply our original fraction by the conjugate. So our conjugate is going to be 3 plus the square root of x plus 4. Okay, simplifying that, multiplying that out first, and then we'll simplify. We get, in the numerator again, I'm just going to leave that the way it is. I'm going to show the conjugate in the numerator. And the simplification is going to come in the denominator. So we get 9 minus x plus 4. Okay, simplifying the denominator. Rewriting the numerator first. The denominator becomes 5 minus x. Now we don't have the exact same factor, but what we want to remember is we can think of the denominator as -1 times x minus 5. So then we can cancel these. So our limit becomes negative, I'll just put it in front because we don't have a fraction anymore, 3 plus the square root of x plus 4. Now we can direct substitute, so we get negative 3 plus the square root of 5 plus 4. So this becomes negative 3 plus the square root of 9. So we get negative 3 plus, this whole thing is negative, sorry, forgot that. 3 plus 3, so we get negative 6 for our answer for this second one. So that's how you use the conjugate method. All right, example 6 starts at the bottom of this page and goes on to the next one. And again, these are ones I'm going to have you do on your own. So again, pause the video. Let me first put the answers for these two, and then I'll put the answers for the next page. Okay, so here are the answers to part A and B, 17 and 5/4. And then moving on to the next page, I'm going to zoom out here on this. I think I made the answers big enough that when we zoom in or zoom out, you can see them. There's the answers to C through K. And again, as I've said earlier, if you did not get the correct answers or not sure how I got the solution that is shown, please ask in class. Okay, so we have one more part, and that is looking at the two last limits that were listed, the sine x over x as x approaches 0, and the 1 minus cosine x over x as x approaches 0. Where do they come from? And how we got those is by using what's called the squeeze theorem, which is our last topic. The squeeze theorem is a technique used to confirm the limit of a function by comparing it with two other functions whose limits are known, easily to compute, and we can put the limit that we don't know like in between the two. We like trap it between the two functions on some interval containing c, the point where we're trying to find the limit. And so what this does is it forces the idea that if we know, as in the picture here, if we know f and h very well, and we squeeze g in between them at some particular point, c, they have to have the same limit because they all meet at that point. So if we know the limit of f of x and h of x are both L, then if g is squeezed in between them, regardless of what kind of behavior g is having, at that specific point c, it also has to have the same limit L. So example 7 is showing if we know that f of x is between 1 and the parabola x squared plus 2x plus 2, we want to find the limit of -1. So here's what we do. Since we're looking, we want to find the limit of f of x as x approaches -1. We know the limit on the left is 1 because the limit of a constant is a constant. So we want to make sure that the limit on the right, the parabola, is also 1. So that would mean if f is between them, it forces them by squeezing it together that f has to have the same limit. So writing this down, here's what we have. We know that the limit as x approaches -1 of 1 has to equal 1 because it's a constant. So now let's also find the limit of our parabola, our quadratic. So we're going to find the limit as x approaches -1 of x squared plus 2x plus 2. So doing that, we get -1 squared plus 2 times -1 plus 2. So simplifying that, we get 1. So what we can see is that since the limit as x approaches -1 of 1 is equal to the limit as x approaches -1 of our parabola, x squared plus 2x plus 2, then by the squeeze theorem, the limit as x approaches -1 of f of x also has to equal that equals 1. So that's the idea behind the squeeze theorem. Let's do one more of those examples. The second one is, now suppose f and g are boundaries of h. So you can see h is kind of a little crazier than we used in the last example. It's the green dotted line in the picture, and it kind of goes all over the place. So the question is, if we know it is squeezed in between f and g, and we're given functions for f and g, so f of x is ln of x plus x squared, and g of x is e to the x minus 1, for all x in our interval containing 1, except for 1 itself. So we want to find the limit of h of x at 1. So it's the same idea. The difference here is that we have to notice is that to the left of 1, here in this section, g is greater than f, but after 1, to the right of 1, f is now greater than g. So we have to consider those limits separately when we talk about the limit of h. All right, so let's find our limits and go from there. Okay. So we're going to start by finding the limit as x approaches 1 of f of x. So that means we're finding ln of 1 plus 1 squared. Ln of 1 is 0, so we get 1. And now let's also find the limit of g as x approaches 1. That's going to be e to the 1 minus 1. E to the 0 is 1. So what we want to do now is, as I said, we have to treat these as a left and right one. So the first case we're going to say is 4x less than 1. That's to the left. We have the situation where f of x is less than or equal to h, which is less than or equal to g. So h is squeezed between the two, but it's bounded above by g and bounded below by f. And since, and this is going to be very similar to what we wrote in the last problem, since the limit as x approaches 1 from the left of f of x is going to equal the limit as x approaches 1 from the left of g of x, and this is equal to 1, then the limit as x approaches 1 from the left of h of x is going to equal 1. So that's our first case. Our second case is going to be 4x is greater than 1. So that's the right hand side. And in this case, what we see is now g of x is the bottom boundary for h. H is still squeezed in between the two of them, and f of x is the upper boundary. So in this case, we can say, since the limit as x approaches 1 from the right of g of x equals 1, which is equal to the limit as x approaches 1 from the right of f of x, it follows then the limit as x approaches 1 from the right of h of x is equal to 1. So now we can put this together, because what we have found is that we have a situation where the right and left-hand limits are equal to each other, so the limit of the function is defined. So we can say, therefore, the limit as x approaches 1 from the left of h of x is equal to the limit as x approaches 1 from the right of h of x equals 1 by the squeeze theorem. And I wanted to make sure I did that example because it's a little different than the first one, because now the functions are moving a little bit and it's just not as straightforward. You have to take into account the idea that from the left you're bounded above by g and bounded below by f, but from the right you're bounded above by f and bounded below by g. So we have to think of those separately. So we'll do more practice of these problems in class. So I hope this video was beneficial.